Now, once you know how the electronic configurations are, and then you have to ask whether it is going to have any orbital angular momentum or not. Those questions, obviously, when you read, you will have, you can verify it by this table. You don't have to verify right now. You can sit down. I hope the table is not wrong. None of the data is wrong. So you should be able to justify the data by itself. This is like a self-check, okay, whether you have understood orbital angular momentum and T2G, EG electronic configuration or not. Okay. Same is true in here. For tetrahedral complex, once again it is the same thing, E and T2, right, E and T2. So E configuration usually will not give you any unsymmetrical filling in E is not going to give you orbital angular momentum, but T2 can, right. So based on that, because E is dx2, y2 and dz2, right. So for example, D1 for octahedral is T2G1, right. That means orbital angular momentum is possible. D1 for tetrahedral is E1, right. It is splitting between E and T2. Is that clear? Any of you did not understand that? I will be happy to discuss again. Yeah. No, this is the spin only value. One unpaired electron 1.73. Yes, usually what also happens is simply the splitting in the tetrahedral. See, you cannot directly compare octahedral versus tetrahedral. You have to also understand the trend in the sense the splitting between E and T2 is less in tetrahedral. This is octahedral. Yes, this is the observed value and this is the calculated value. That's the maximum you get. Okay. Yes, expected is you should get little bit higher than that, but it doesn't because some quenching is there. It is more. See, we are not going to trick you that observed is less than the calculated. That can happen sometime. We'll see more. There could be some other contribution, quenching by spin exchange, which I will be discussing. Okay. What I am mainly trying to say is spin only values should be good enough, but when you see the value is more than the spin only value, then orbital angular moment perhaps is there. How to calculate it? Simply by figuring out whether you are having orbital angular moment or not. If you experimentally see the value is little less or exactly similar or very close, that means that some other way of quenching would be there, which will be at least one instant we will be discussing today. Okay. It's, this is like too simplified in terms of teaching. Okay. In reality, you can have a lot of other practical components which maybe we are not discussing. But once again, for this class, we are saying that only thing you want to worry about is the spin only value. After that, if you find that the value is little bit more, sometime 0.1 more, 0.2 more, those are originating because of orbital angular momentum. Okay?
Why is that orbital angular momentum component always adds up to the spin angular momentum?
Because no, orbital angular momentum will always add up. It depends on the directionality, right? So if you are imagining, let's say, more of a spin up, and then it is another vector is there, two direction. Whatever this vector is having, and I mean vector addition is usually you are going to take the modular value, the absolute value.
If the spin has component up, if the spin angular momentum has one component which is pointing upwards, then why is
That's a good question again. We usually never actually worried for the orbital angular momentum versus spin. Usually we deal separately and then take the pure value of it, do the vector addition. Okay. Now if you want to do the, see it is orbital angular momentum actually doesn't depend on the spin, right? It is the motion around the orbital, right? So spin only value is dependent on the spin. So therefore up and down is coming. Orbital angular momentum, there is no spin component. No, that is the motion. Simple the motion is we are discussing, right? Simple motion. It's not the up and down motion we are. Up and down motion is the spin. I think that perhaps is the reason.
It means that it doesn't matter if we consider electron to be going like this or going like this.
No, so let's say some spin are up and some spin are down. Okay. So orbital contribution for all those will be taken as just the orbital contribution, right? Up spin and down spin, what is the orbital contribution total we are seeing, but we are not mixing up that with the spin value. Spin only value is separate and orbital value is separate. Okay, let's calculate. Sorry? Where between the orbital and the spin? For that spin only values, n into n plus 2, mu L plus S. Okay, the main equation, the first equation, that is assume that it is 90 degree. I think that is independent of the angle. Why we need an angle for that? Well, the spin, I don't think spin and the orbit are, of course spin orbit coupling can be there, both the coupling can be there, but if you are individually taking how one is affecting the other, if direction doesn't matter actually. Sorry?
Direction is not really fixed, that is why we get the range of the US plus minus mu.
Yeah, that is mainly, so that is when we have, yeah, we usually say that when it is less than half field, that is L minus S we take. When more than half field, then we take L plus S values. I think it is independent of the direction, right? Okay, I will try to find out if it is dependent, if the equation is dependent on the direction. Okay, let me proceed further. Okay, we have dz2 and dx2y2, which is not interconvertible, and we are started saying that for d2, these are the value, and then we are saying that these are the orbital contribution, whether possible or not. Yes or no answer. Now same way it is true for tetrahedral complexes. Okay, you can find out whether it is there or not. If there is any discrepancy, then just let me know. I think this should be this is from the book directly. Other reasons for orbital contribution. So usually we are pretty much focused on the ground state electronic configuration. Sometimes what happens is, let's say T2G6 EG1. T2G6 EG1 means there should not be any orbital contribution. But still, if you can excite T2G6 EG1 to T2G5 EG2, one of the electron from T2G level to EG level, if you can promote, then you can promote or then you can induce orbital angular momentum. Okay? That is where we are talking that excited state can sometime also contribute. Okay? This excited state contribution will not be as high as the ground state contribution. Okay? So for example over here T2G6 EG2, no orbital angular momentum should be there, but in excited state it should be T2G5 Eg3. Now orbital angular momentum will be there. Of course, the absolute value will be less compared to if some other compound is giving from its ground state. Okay? So the orbital angular momentum not necessarily coming just from the ground state, it can come from also excited state. So therefore, this leaves a option, or this gives a option to set a question saying that, look, the spin only value should be this much, or you calculate the spin only value, which is, let's say, 1.73 or 2 or 4.89, whatever it is, but the observed is 5.6. You do the electron distribution and see there is no way you can have orbital contribution, orbital angular momentum, but still the value is high. Then of course you have to think perhaps ground state is not contributing, there is a chance maybe in the excited state. Okay? So under the normal condition, if you cannot explain what's going on, then you are open to include the excited state. Same is over here, E4 T23 should not have any orbital contribution, orbital angular momentum. Now in excited state E3 T24 you can have it. Okay? In all these cases you see that mu observed is greater than mu spin only. Okay? For both octahedral nickel 2 plus and tetrahedral cobalt 2 plus, because these are the electronic configuration for octahedral nickel 2 plus, that is there, tetrahedral cobalt 2 plus, that's there. So at least these two terms should be very familiar, octahedral nickel 2 plus, tetrahedral cobalt 2 plus. These are the one can give you excited state. Other than that, if any question is given in the exam where you cannot, once again, cannot explain by normal understanding of orbital angular momentum, like unsymmetrical filling in T2G, it is symmetrically filled, still the value is high, you can try to explain that by contribution from excited state. Is it clear? Okay, you read it, it should be. Now this is how it is. So T2G6 Eg2, now one of the electron, if you can convert, if you put, let's say light, if you put energy or the distance between these two is not very high, in excited state you can achieve, therefore from T2G6 Eg2 you can have T2G5 Eg3. Now in this configuration you can have the orbital angular momentum. It's clear? Both ground state and excited state you need to consider. Now this is another configuration. Okay. This is for T2G5 Eg3, I guess this is the one. Of course, in here you can have three different orientation, that's what we are trying to say. So not from ground state, if you go to excited state can have three different configuration, right, which is the origin for orbital angular momentum. Okay, no need to have this point, just this is good enough. Ground state there is no orbital angular momentum, excited state it should be there. How it is coming? I think you have already learned, because the relative positioning of the electron can vary. Okay. Now, so what we are trying to tell you here is, this is also a D8. This is also a D8 configuration. Nickel 2 plus is D8. Nickel 2 plus D8 octahedral case. This is the scenario you have. Nickel 2 plus D8 tetrahedral case. What's the electronic configuration? Nickel 2 plus octahedral and tetrahedral. Nickel 2 plus D8. Octahedral will be, this is the electronic configuration. Okay. Octahedral with not so strong field ligand. Strong field ligand should have given you the square planar geometry. This is nickel tetrachloride or nickel hexaaqua or whatever. Weak field ligand should give you the octahedral species. Okay. Whenever you see D8, be little bit cautious. D8 can have octahedral and tetrahedral. octahedral and square planar. Of course, if it is given clearly, that's no worry. D8 electronic configuration with strong field ligand like cyanide or carbon monoxide can give you square planar geometry. Sometime for these cases you do not have to worry, but in other cases you have to worry a little bit. Now nickel 2 plus octahedral electronic configuration is given. Nickel 2 plus tetrahedral electronic configuration is D4 T24, E4 T24, right? So E4 T24, right? Now the question simply is, which one will have higher orbital or higher magnetic moment value? Both of them are having 2 unpaired electron. Here you have 2 unpaired electron, here you have 2 unpaired electrons, right? Octahedral, tetrahedral, both of them are having 2 unpaired electron. Experimentally, which one you think will give you higher magnetic moment value? Tetrahedral. Why is that? Simply because this contribution for octahedral, this orbital angular momentum contribution coming from the excited state. In the ground state itself, there is no orbital angular momentum. In the excited state, there is. But in tetrahedral case, you can have orbital angular momentum due to the unsymmetrical filling of the T2G orbital, right? That's the reason. And actually it can go up to, for 2 unpaired electron, it can go up to 4 Bohr magneton. Okay, Bm is the unit for magnetic moment. Okay, it's okay, it's given. Now, so far we have discussed about the D block elements. No, that also depends on the ligand. Strong field, if the ligand is strong field, usually then only you will see. Okay, so if it is a weak field ligand, then you don't see too much of that. Okay, all right. Now, weak field means fluoride, chloride, water. These are the weak field ligand. You have that spectroelectrochemicals or spectrochemical series, right? It's not spectrochemical series. Now, so far we tried to discuss the magnetism of D block elements. We have simply learned spin only is good enough. Some few special cases we have said that orbital angular momentum is essential, and thereby values can increase. If, once again, I think that's a valid point, that if you see little bit decrease, don't worry about it, because there may be other reason. We are not worried about less value or lesser value of an experimentally observed magnetic moment. We are mainly worried about the higher value. Lesser value can come from a lot of other factors. Now we are now trying to discuss the magnetism or magnetic behavior of lanthanides or actinides. We will not get into actinides, just simply lanthanides. So simply speaking, lanthanides are of little bit different class of compounds. Okay, it has F orbital. You know that F orbital is buried inside. It's not the real outside electrons are the S, even wherever if you see lanthanide, cerium, praseodymium, whatever EM or whatever that 14 are there, CPR, EM, SM, samarium, gadolinium, whatever it is there, all of those cases F electrons are buried inside. What essentially that tells you is ligand will have very little effect. Ligand cannot influence the magnetic moment value. Because the F electrons are buried inside, ligand cannot affect the F electron too much or almost nothing. So D orbitals or D block elements, we were seeing that orbital angular momentum value are almost gone. right? That mu L component is very little, only when unsymmetrical filling is there then we are seeing. But over here you do not have to worry about anything, you have to do both L and S component, orbital and the spin component, because orbital component cannot be restricted by the ligand. So as if you are dealing with a free metal species. Although metal complexes are there, lanthanide complexes are there, lanthanide ion is in the middle, ligands are surrounded, but ligands cannot affect the magnetic moment value. But you have seen that for octahedral complex or tetrahedral complex or d block elements, ligand can influence. There is a splitting in the d orbital. F orbital we do not see such splitting, or you can take it almost that there is no splitting in the F orbital, because ligand and F orbital cannot interact too much. That's fine. Therefore, you have to bring back your previous equation which has magnetic moment values by considering both orbital and the angular component. Okay? Now, the facts, that is the fact that F electrons in lanthanides are buried in the n-2 cell. So, you are in for calculations. What is the calculations? Let me show you. This is the calculation. Okay? This is something I guess you have to know, if not remember. I think a lot of you know this already. Okay? Start learning. Now, so number of unpaired electrons, that is that component can give you the S, summation of number of spin of the unpaired electron. That is S, you know. L, this L you know from these ml values, right? Let me. So term symbol you have heard of. So I will discuss a little bit. 2s plus 1 Lj, j equals L plus S or L minus S, absolute value of these. Now S equals number of summation of spin, right? Or whatever way that is written, summation of spin, let's say, number of unpaired electron. Let's say you have 3 unpaired electron. 3 unpaired electron, that means spin will be, S will be half plus half plus half. Right. Now, if you have 3 unpaired electrons, so this is your F orbitals 1, 2, 3, 4, 5, 6, 7. So ml values are plus 3, plus 2, plus 1, 0, minus 1, minus 2, minus 3. Right? 3 unpaired electrons simply means that. Right? ml maximum. 3 plus 2 plus 1. So L equals 6. 3, 2, 1. Okay? Now therefore, for that case, 3 unpaired electron case, you have 6, this L value at 6, I will come back to that. You know SP term symbol, SP, D, F, G, H, I and so on. So S, L, if L value is 0, then that is S. If you have not studied before, you just go for this Russell-Sanders term. S, P is 1, D is 2, F is 3, 4, 5 and so on. 1, 2, 3, 4, 5. Now, this capital S, you have learned 3 by 2. 3 by 2, right? 3 by 2, it is going to be 4. So 4, 6 is going to be I. Okay, I will come back and explain in a moment. And J. J is L minus S for the less than half field configuration. So J in this case will be 6 minus 3 by 2. that is going to be how much? 9 by 2. So this is going to be your term symbol. Okay? Although you don't need to really know this one, like this J term for the class, but I think some of you, at least 30% of you know, or 40% of you know, I don't know. Okay, so what we are trying to tell you is, this is the Russell-Sanders term symbol, kind of derivation. What it tells you, the total spin, let's say you have F3 electron, 3F electrons, F3 configuration. Okay, see here, EM. So what's that? 3 plus will be C pair EM. EM is what is the Einsteinium? No, EM. EM is Einsteinium maybe. Anyways, praseodymium is 2 plus is going to be F2. I think EM is going to be 3 plus. 3 unpaired electron. Anyway, 3 unpaired electron if you have, that 3 unpaired electron will give you spin value, S, capital S is going to be 3 by 2. You have to calculate the L value. L equals summation of ml, 3 to 1. So that is going to be 6. S you know, L you know. J equals L plus S or L minus S. L plus S when it is more than half filled, more than F7. Okay, and L minus S when it is less than half filled. In this case, 3 unpaired electron less than 7, F7, so L minus S, L minus X, that is becoming 9 by 2. Okay? Now you left up with just this one, 2S plus 1 LJ. 2S plus 1, S equals 3 by 2, you plug that in, so that is becoming 4. Okay? L is your 6. That means, that 6 means if L equals 0, that is S, if L equals 1, that is P, if L equals 2, capital L equals 2, then D, F, G, H, I and so on. So from there you get I, and then J, in this case we have calculated L minus S. Some of you who knows this, that's fine, no problem for you. Those of you who didn't hear it before, just Google it, you will be able to get it clear. I will show you one over here with praseodymium 3 plus. Sorry, L plus S?
We calculated L minus S.
Yes, because less than half filled.
Less than?
F7, yeah. Okay, now let's look at here, okay? Whoever knows, can you please calculate by yourself? Praseodymium 3 plus, I am saying that electronic configuration is 4F2, F2, okay? F2, can you calculate? Whoever knows it, calculate. Whoever doesn't hear this before, stay with me, I will explain, okay? Now F2, that means 2 unpaired electrons, right? 2 unpaired electrons means spin equals half plus half, total S equals 1. Are you following me? Okay, fine, if you get it right, the answer is given here, definitely. Now L equals, so 2 unpaired electron, it should be plus 3 and plus 2. L should be the maximum also, right? It is not like you will put at 0 and minus 1 or anything. So that is L equals summation of ML. ML is what? Plus 3, plus 2, plus 1, 0, minus 1, minus 2, minus 3. 7 of them, 7 orbitals of F. For D, it was plus 2, plus 1, 0, minus 1, minus 2. If it is degenerate. Okay? And so on. For P, it will be plus 1, 0, minus 1, if it is degenerate. Anyway, so this is the L value. Summation of ML. 2 unpaired electron, 3 and 2, 5. Now J will be, in this case, since it's half field, less than half field, less than 7 electrons, F can have 14 electron, 2 is less than half, less than 7, so L minus S, 5 minus 1, 4. Okay. Now if you have that here, praseodymium 2 plus, 3 plus is 3H4, I think you have calculated, right, 3H4. How? Now you plug it in this equation, 2s plus 1 Lj, 2s plus 1 means 2 plus 1, 3, L is going to be 5, that is going to be H, so 3H, is it getting clear? Okay, let me just, some of you may not be seeing it. Okay, it is going to be 2s plus 1 Lj. So 2 minutes break you can take, you can go for whatever. 2s plus 1, S equals 1 plus 1, L equals 5 and J equals 4. So this 5 is going to be 3 and 0 SPDF SPDFGH, good, and 3H4, 4 is 2J plus 1, sorry, L minus S, is it correct? Okay, break. Okay, let me start. Okay, I think this math part is way too simple for you guys. It's these two equations are there. You calculate Gj first, Gj with S and L value and J value, and then plug this into this equation, that's all. For your verification, that is the table. You should be able to calculate 2-3 of them by yourself to get confidence, nothing else. The values are given, equations are given, unpaired electrons are given, L, S, J value you should be calculating by yourself. Then mu value, calculated value, don't worry about the observed value too much, just calculate the values. You should be able to get exactly same values, unless anything is given by mistake, any wrong data are given. I don't think any wrong data is given. Okay, so once again we are talking about the lanthanides. F orbitals are not perturbed by ligand. Therefore, both L and S component, orbital and spin component of the magnetic moment you have to consider. Simply you have to know these two equations. What are those two equations? These are the two equations. What is S, what is L, what is J, that you know. Once you have that, you have Gj calculated, you put that Gj value and the J value you have already calculated from there. You put all these mu value you should be able to get. Those mu values are calculated and shown in here for given electronic configurations. For different electronic configuration it is given. So you, sorry? Oh, that's mistake. Delete that mu b. Okay. It's the calculation is shown for praseodymium, PR 3 plus. You can see from, for just clarity, one of the example is shown here, praseodymium 3 plus, which is F2 electronic configuration. You can calculate this one first yourself and then go on to calculate any of these. Okay. This is, you don't really have to worry about this bottom term. You can just calculate the just 1s, 2f, 3h and so on for the class purpose. But as you know, this is very simple, 2s plus 1 Lj. This j you don't really have to worry. J equals L plus S or L minus S, but still I would say you should do it. For the class purpose you may not need to worry. Less than half field electronic configuration, L minus S. What is the half field? Half field 7. L plus S will be for the more than half fill, and from there you can get this term symbol, Russell-Sanders term symbol it is called. Okay. Now let me move on. So this is the experimentally calculated value, sorry, theoretically calculated value, this is the experimentally observed value. It is quite close, that's good enough. Okay. Here you do not have to worry about any orbital angular momentum because you are already taking care of it. You are calculating based on that. Okay.